So I'm Philip Ball, and I'm here to talk to Lindy Elkins-Tanton, who is the head of an extremely exciting forthcoming space mission. That I guess, I mean, correct me if I'm wrong, of course, Lindy, but it's primarily a NASA mission, right? Called Psyche.
A NASA mission, that's right, called Psyche. Exactly so.
Okay, fantastic. Well, I want to start. I mean, I have so much. I've got 4 pages of questions that I'm going to get through here, and I don't have any hope really of doing that. But let's see how we do. But I want to start there because this is clearly going to be what's in the forefront of your mind at the moment. Because as last I heard, the launch date is 5th of October, right? Is that still?
That's right. That's right. We have what's called a launch period, and it opens on the 5th. That runs through the 25th. We have 21 days on which we can launch, and we surely hope to launch on the first day, October 5th. That's exactly right.
Fantastic. Sorry, I should have also given your institution. Are you still at ASU?
Yeah, I'm a professor and vice president at Arizona State University.
Right. Fantastic. Well, I hope that you can start by telling us, what is Psyche? What is Psyche, the object out there in space, and what is the Psyche mission?
Yeah, we are interested in how rocky planets form and how they get to be in the structure that they are, with a metal core and a rocky exterior. And it turns out there's one place in the solar system that we can go to learn about the metal cores of rocky planets, and that is, ironically, this asteroid Psyche, because we're never going to get to our own planet's core, or the cores of Mercury or Venus or Mars, or the moon has a core too. We can't get to that either. Too hot, too deep. But there are about 9 asteroids that we think are made mostly of metal. And the very biggest one, and the only one that's kind of round-ish, I say is shaped like a potato, because potatoes come in many shapes, and we'll find out when we get there, is this asteroid Psyche. And so we're sending a robotic probe to go find out about a new kind of world, a world with a metal surface.
How big is Psyche?
It is about the size of Switzerland or Massachusetts without the Cape. It's the surface area of it is about the same as the state of California, and so it's a kind of a human-sized asteroid, though large among asteroids.
And really, it's essentially a lump of iron and nickel, right?
We think it's a lump of a mixture of iron and nickel metal and something else. And we think this something else is probably silicate rock, but it could be sulfur. And also there could be pore spaces and, fractures. So we'll find out when we get there. This is, the fundamental thing about this is primary exploration of a kind of world humans have never seen. We don't have any photos of its surface. And probably everything I tell you today is going to be wrong when we get there. So we'll all discover together what it is.
So were you implying just now that we don't really even know what it looks like, what shape it is?
That is exactly correct. Yeah, we've got pretty good models of its shape based on how radar sent from Earth reflects off it. We can actually shoot radar out to the asteroid belt and receive the returns, which amazes me. And also reflected light from the sun. And so people put that together in computer models, and they make shape models of Psyche. Triaxial ellipsoid, they say, like it's like a football or a potato, but we don't know the details. We've got no photographs of its surface. And this is something we're not used to. We're used to being able to just Google the name of an asteroid or a planet and up come photos, but there are none for this one.
I mean, it conjures up, when you think, okay, it's made of iron and nickel, it conjures up this image of this shiny thing in space.
Yeah.
Likely to be shiny?
No, sadly, not likely to be shiny. Although, in my dreams, it's a polished slab of shining meteorite metal with gleaming inset gold and yellow crystals. But the truth is, it's been hanging out in space for 4.5 billion years, and it's probably not shiny.
And you say that this is what we think planets like ours have at their core. So how did this bit of core-like material get to be floating around naked, if you like, in space?
Yes, I know, a naked core in space. It's so unseemly. So we think that all right, so we ask ourselves, how do you get a lot of metal in one lump? And the best guess is that it's part of the core of a planetesimal, a little tiny planet that formed in the first eye blink of our solar system. So our solar system is 4,568 millions of years old. And in the first 2 of those millions of years, So if the solar system was a 24-hour day, like in the first 15 to 30 seconds, bodies the size of states, big cities or states or even continents formed. And they formed and they were round objects, we know, because the remnants are in the asteroid belt. Most of them went on to form the rocky planets that we now call home. But some of them got shattered and stranded in the asteroid belt. But before that happened, way back in those first 2 millions of years, some of them melted. They melted from short-lived radioisotopes, particularly aluminum-26, which is extinct in the present day, but was very heat-generating then. And the material they were made of was intimate mixture of metal and rock, centimeters, millimeters. Once that's melted, the densest part, which is the metal, by a factor of 2, sinks to the middle, and the rock is left floating on the outside. So that's our favorite idea for how you get a big lump of mostly metal. Then you knock off a lot of the rock with impacts. Is it the only way that you could make a metal-rich body? No, there's other ways too, but they're all hypothetical. We don't have any examples. So it becomes, you can't use a normal distribution idea of processes for an object of which there's only one. And so we're faced with trying to apply Occam's razor to this singular body. And I mean, it might not be well known that what William of Ockham actually said was you should choose the simplest hypothesis because it's the easiest to test. He didn't claim it was the most likely. He just said it was the easiest to test. So our hypothesis is that it's part of the core of a planetesimal that formed in the first 2 million years of our long-lived solar system.
So as well as giving us a view of this weird world like nothing we've seen before, the hope presumably is that this mission is going to tell us something about how the planets, how the solar system itself formed.
Yeah, that's right. One of the most fundamental questions that we have as humans is, why were we able to come to be on this beautiful planet Earth? What is it about Earth that makes it habitable and conducive to life? One of the things that does is the metal core. And so what it makes our magnetic field. It helps to protect our atmosphere. It's the repository of a lot of the heat that comes out through volcanism and plate tectonics in our planet. And so how do you learn about a core you can't reach? And effectively, it's like a cooking metaphor that I like to use. Effectively, our Earth is like a cake. It's already had the eggs and the flour and everything beaten together into a mixture and then baked and frosted. So how do you back out what are the eggs and what was the flour? By looking at the cake. And so with Psyche, we'll be looking at one of those original ingredients, one of the ingredients we've never seen before.
Right. Fantastic. I know that, well, of course, the universe and the solar system is full of objects that lots of people would love to go and take a look at. We can't go and look at them all. So I know that getting to persuade an institution, a body like NASA, to actually let you do this, to go and see the thing you want to see, is incredibly difficult. And your book makes it quite plain, what a tortuous process that is. How do you do it? How do you persuade them that this is where they want to go and not somewhere else?
Well, I hardly need to tell you that the way to persuade a human being is with a human narrative. You've got to have a story. It's got to be a story that brings you along and makes you feel a part of it. And it's especially hard to tell a compelling human narrative about an object that we've never visited and we have no pictures of. And so one of the things we had to do was create art based on the science that we felt was the most likely, to show people what we might see and inspire them to want to be part of it. And to, well, partway through this gigantic 3-year competition process, we were once again being asked by people on the engineering team, wait, why do we want to fly this instrument versus that instrument? And we, the scientists, and in fact, the media people also realized that we had this videotape running in our heads of how we thought that Psyche had formed. The body formed early in the solar system, melted, formed a core, and then things hit it and knocked the rock off. And that is all of the motivation that we needed for the science that we were choosing. And we realized that no one else had that narrative in their heads but us. And so we created flip books and videos and tried to write it out in prose, how we thought this body was formed and why it was important to us now. And so then you have to do week-long review processes with the external review board, and we wrote over 1,500 pages of proposals, and you go through 2 gigantic gates, one where they knocked 27 proposals down to 5, and then the second one where they knocked 5 proposals down to 2 and selected us for flight. So it is an epic process, and if I might just finish up this comment by saying, I've never imagined that I would be working on a project that was a 20-year project. So we're 12 years into what's going to end up being a 20-year project, fingers crossed that it continues to go well. And one thing I've learned is that not only is no part of it a sprint, except for the occasional emergency, or it's that it's marathon after marathon. So the first marathon is getting Jet Propulsion Laboratory to be our mission manager and put us in their portfolio. But then that's just the beginning of the next marathon, which is the huge competition process. Then we get selected and we feel like that's it. But no, that's just the beginning, because now we have permission to build it. So God willing, we launched successfully on October 5th. That is a big finish line and the beginning of a giant marathon as we send the spacecraft out to actually do its work.
Fantastic. Well, I'm hoping that we'll be able to loop back to Psyche at the end, because I want to ask some more about it. But I want now to go right back to how you started in science. I mean, I think you and I are probably near contemporaries, and so I remember what it was like as a young person, these days wanting to get into science. But in particular, I remember, and it's clear from your book that as a young woman, you really weren't encouraged to do that in those days, but you did. So what drew you to what convinced you that science was going to be your thing?
It's such a complicated story, and it was only just recently, within the last couple of years, bizarrely, that I really felt like I inhabited the identity of a scientist. I always was interested in the natural world, but I was interested in many things. And you're right. There were discouraging aspects, and people who thought I wasn't smart enough, and comments about women in science, and weird how gendered our brains still are, men and women, despite our efforts. I think that the possession of bias about who can do what is not gendered. Everyone seems to have the same bias, men and women alike. And so we're biased about ourselves and we're biased about others. But then there were other voices in my life saying, absolutely, you can go ahead. And so it was nice to have kind of a mixture. And the thing that really motivated me in the end was teams, was how much more you could do to try to answer great big questions when you were able to work in teams where everyone could rise on their merits. And that is a little antithetical to the traditional hero culture of science. And I wonder if you ever reacted also to that sort of hero culture of science, where each person is meant to be self-aggrandizing and learn how to speak like an expert and shut down the competition.
Absolutely. I mean, that's something I want to really go into some more, but it's completely what I have experienced, and it's for a long time, and I think still actually within science, it's how the history of science has been told. That I think scientists, to make a broad and probably unfair generalization, they're still quite wedded to the great man, idea of science, which historians have thankfully got rid of long ago, but in science it's still there, and of course it's almost
still there.
And it's a peculiar thing, and it's particularly, I mean, what strikes me as most peculiar is that at the same time scientists will insist that the individuals don't matter. It's the ideas that that we worship in the end, or that we revere in the end, but somehow individuals get statues made from them and things named after them and so on. So there really does still seem to be this hero culture in science.
That is so right. There's the myth that what science does is remove the person from the observation and the decision. But the truth is, everything that humans do is about the humans that are doing it. So, and there's still, I don't seem to particularly have this need, but there are people who really have a need to have heroes, to be able to point to someone and say, look at that amazing thing that they did, and to be super impressed. But the thing that I really love is the feeling of people doing things together. And it turns out, fortuitously for me, that at least in part, the era of the hero scientist is past. You can no longer make fundamental chemical discoveries in your kitchen like you used to be able to if you were a lord and had the time and the money and the kitchen. And so now the really biggest things are things that have to be done in interdisciplinary teams. And so that's fortunate for me because that's what I really love.
Well, okay, that was what I was going to come back to later on, but you've gone there now. So let's stick with that. Clearly that's such a crucial part of a project like Psyche. The team clearly is massive. It has to be. And you have some great advice in your book for how to do that, how to cultivate a team spirit. What are your top tips for trying to do that?
I have tips to share, and then I would like to share the ways in which I've totally failed to actually implement this because it's such a learning experience. I think that the most important thing we can do is work to include every voice. It's very common in kind of top-down, dare I say, like hero culture kind of teams where the leadership are the only ones who really are allowed to speak. But the person who authentically knows what's happening, the boots on the ground worker who is actually writing the code, soldering the piece, whatever it is, they often don't have a voice, but they're the ones who know when there's trouble. And so there are three compelling reasons why teams should always send the question to the person who authentically knows and encourage the shy person to speak and draw out the person who feels like they should be sitting against the wall instead of at the table. The first one is just ethical. I assert this shamelessly. This is the way humans should be together, allow each person to rise on their merits and shine. And it leads to diversity, it leads to equity, it leads to inclusion, things that are ideals of mine, and I hope of lots of people's. The second reason is risk buy down. If you really want your project to succeed, you have to discover the problems while they're still solvable. And the only way to discover them while they're still solvable is to invite people to speak about them. And so project success lies upon this kind of idea. And then the third reason is, so when I've had to, these are the same three reasons why you would want to reduce sexual harassment or bullying or any of the sort of ills of human nature. And the third one, which is sometimes the one has to resort to in moments of desperation, is the legal system. It will help you avoid lawsuits if you do this. And so there's ethics and there's project success, and then there's the legal side. And so that's my number one thing, is like try to make it so that every person can speak.
Right. So it's not just the right thing, the proper thing to do to work this way, but actually you're saying, and it seems that experience bears this out again and again, it's the most effective way. It's the most likely way to lead to success.
Yep.
Yeah. And I guess within that, there's it sometimes feels to me as though there's still a sort of template for what it means to be a scientist and a successful scientist. There's a way to be, whereas I think more and more people who work in teams come to recognize that you absolutely need people with different skills. You don't want a team full of, individualistic geniuses. That would be disastrous.
Yeah. Turns out it doesn't work well. Yeah.
So you need people who are good at forging connections between others. You need some people who will just drill down into the details. You need, technical people to know what they're doing, as well as theorists, and so a whole range of different skills. Basically, There's a single intellectual mindset that you want.
That's right. Skills and behaviors. And so we absolutely need disciplinary experts, completely necessary, but that's almost a separate category of what we need from the things that you and I are talking about right now. You need people who are willing to listen to and speak to each other. You need people who keep a calm voice under moments of crisis. There are so many ways to shut down teamwork, including passive aggression, unnecessary self-aggrandizement, all the sorts of things that you can kind of point at as obvious bad behavior. But then you need to also have, in addition to sort of good behavior and collegiality, you need people with that tacit knowledge, in the Michael Polanyi sense, It's the knowledge that is hard to articulate in words. It's in gestures, it's in intuition, the way that you can make a thing or do an experiment that you can't really learn by reading a procedure book. You need to be shoulder by shoulder by the person to learn from them for that. And so you need people who have the tacit knowledge and the explicit technical knowledge, and that can get along in a group. And these are things that you can practice. And I would just say that the antithesis of that was actually, I think, brought to perfection in the German academic system of the 19th century, when they did actually explicitly realize that one of the ways that professors become successful is through charisma and strength and determination of their assertiveness. And that way they got more paying lecture students and more fame, and therefore brought, material and resources and interest to the university. And so there was the realization that the hero, the superstar, the influencer, faculty member brought good things to the university, but it trains a kind of person who doesn't work well in teams.
Right. Yeah. Well, I was very struck by that. Certainly, throughout the 80s and 90s, when I encountered the German system, that it was, the professor was God, and
Yes,
there was no question his word, almost always his word. I don't know if it's still entirely like that now, but I sort of have the impression that they haven't completely shaken off that way of working. But yeah, I absolutely know what you mean.
Yeah, exactly. And just to add to that, we modeled, a lot of our American universities have that same model because it was modeled on that idea. And a friend of mine from graduate school became, at the time, the youngest woman ever to attain the full professor status in the German system. And so she got an entire city block of buildings with a museum and 1 million laboratories and a library and a whole bunch of permanent faculty that reported to her, and a giant budget, like the whole cake. And so, being ignorant but a little bit of a German speaker, I said to her, so do I call you, because, the male professor is Herr Dr. Professor. And so I said, do I call you Frau Dr. Professor? And she said, no, that's the professor's wife. There isn't actually a word for me. So I felt like that kind of summed it up.
Okay, I want to go back now. Again, you studied geology. You first of all studied geology at MIT, and one of the things I loved about your book was the way you make that subject come alive. I felt I felt like it was as though the minerals become clues in some sort.
Oh, yay! Uh-huh.
Now, the curious thing I always find about geology, in the 19th century, in the early 19th century in particular, geology was the science. With that was where the big questions were. Questions about ancient pasts, questions about origins, and of course, it was central to what Charles Darwin was doing. But you mentioned that today it's sometimes dismissed as the thing you do if you're not good enough for the hard sciences.
Isn't that fascinating?
What do you think that is?
The history of the natural sciences is certainly fascinating to you and me, and I, would like to believe it's fascinating to everybody. I don't know. Darwin, everybody knows who Darwin was and how famously he was the companion of the ship's captain, who just then happened to be a natural scientist and got seasick all the time and ran around on land and learned all these things. And a lot of what he was doing was based on the work of Lyell, the geologist. And in fact, Darwin would have Lyell's latest volumes shipped ahead so that he could read them from his next port, because it was so influential about time periods. Because Darwin's evolution doesn't work unless you understand the length of time there is involved, which hadn't been understood. So that was this sweet spot in history where it was the conflation of the time when a naturalist could make huge progress by simple observation and inference, and where the complexities of geology and biology and the timeline were coming together, and also the way that interacted with the zeitgeist of the time, trying to understand religion and whether there was meaning in life, or whether things were just impersonal and timeless, and that what we did right now really had no meaning. And so I think there was this beautiful conflation of all of these complex thoughts. And then progress started being made in physics and chemistry in particular at a very high speed because of its straightforwardness. In a sense, geology is such a complex mess of biology and chemistry and physics and mathematics and ecology, and everything has to be kind of mixed in. and it's easier to make progress in a science where you can be more specific and narrow in your inquiry. And so I think that a bit left geology behind. And I think it's getting a little different attitude toward it now because of the climate crisis, because geology is deeply involved in how planets work. But the last thing I would add here is that it's very hard to do what we think of as the classic scientific method, where you do multiple experiments and then someone else does the same multiple experiments. There's only one Earth, and we can't make a new one. The problem with the time length and the length, the scale of temperature and time and length makes it impossible to do repeat experiments. So it's much harder to know with absolute forever certainty.
Right. And that's, I guess, also where it comes down to searching for clues about huge things, huge events in the past, in tiny traces left in rocks, isotope ratios or something that, it seems extraordinary. It still seems extraordinary to me that, you can draw such big conclusions about past events from what seem like such minimal differences in the physical object that you're looking at.
Yeah, this was something that frustrated me a great deal during my PhD, because I was really doing experiments in the lab about the chemistry of rock materials. And I began to realize that the interpretation of the results were non-unique. The physicists could find different processes that would lead to the same things that we were measuring. And that non-uniqueness made me realize I've got to learn a lot more of the physics side to try to put these disciplines together to get better answers. So that was a good lesson for me toward moving toward teams. Right.
Well, maybe this will touch slightly on that, but you had a very non-traditional trajectory as a scientist, right? Yeah. So, Dan, you did a master's when you finished your master's at MIT, you went into business for some time.
I did.
What led you to do that? That was something I kind of wondered about in the book. It sounded as though perhaps you doubted, but maybe there was some doubt about whether you were cut out to do science, whether you could. In that environment, was that what it was?
Yeah, I had a really exceptional lack of confidence at that time. I had a lack of confidence that was so profound that I can't even really access it anymore. I try to even remember what it felt like. I only know the fact of it. And I think that it was actually much more related to what I in the book, describe as post-traumatic stress disorder from some fairly horrific childhood events, and which I really not dealt with. And it took me in my 20s to work through that and recover from it, which miraculously did happen. And so when I was very unconfident about my ability to do science. I'd written a very nice master's degree that did get published and was, until I think this year, my most cited paper. It's been cited hundreds of times, but I was terrified of the idea of standing in front of a poster at a conference and be asked questions. It was just, and I can't remember what that was like, but I did. And so then when I was 31, I was not your picture of success. I was depressed and anxious because I hadn't finished solving my problems. And I was recently divorced and a single mother. And I went back to grad school. And amazingly, the faculty member I'd done my master's with accepted me back after I proved to him my brain still worked and took my math, GREs, and all the rest of it. So not at all the picture of success. And to me, that was one of the big reasons I wanted to write the book, because, again, I guess trying to get away from the hero narrative. Right at this moment in my career, I look like a picture of success. I'm now in the National Academy and I'm leading this mission and we're going to launch on a giant rocket and it's looking like things are good for me. But the point of my story is that there's no such thing as just a straight arrow shot from you're born and then you're successful. Everyone's life has these ups and these downs, these crises and these tragedies that you have to deal with, and these moments of brilliant happiness. And life is a ride on the ocean. And so I didn't want at all my book to look like I arrived in this moment, somehow fully fledged. I came from very unpromising and crooked path beginning. And I certainly don't expect to be this picture for the rest of my life. I'm expecting more waves on my ocean.
Well, I think that's one of the most valuable things I found about your book, that it does explain that, you know, there isn't a set way to do this, but also that you comment on the fact that there's a pressure perhaps to create a fiction that is the way it works.
Yeah.
You said that you felt there was a sense that you were supposed to say, you know, I've always wanted to do this. I've been driven. You had to show, you know, a sort of steady pattern of working towards what you're doing now. The fact that you had, you know, taken, if you like, what turned out to be time out and worked in a completely different area of business wasn't seen as a plus at all. It was something that kind of skate over.
Yeah,
that seems that seems such a shame, that, you know, that it gives this impression that there is only one path that you are meant to follow in order to be a successful scientist.
Yes.
And I'm sure that, well, I know that you know, from others, that your experience, you know, you had your particular trajectory, but there are plenty of others who found their way through non-traditional routes, if you like.
Absolutely.
It does seem, you know, a shame, to say the least, that isn't the value of that actually isn't recognized in science.
Yeah, you know, for myself, when I'm looking at young people who maybe want to come and work on a graduate degree with me or something, I don't need them to have known since they were 6 that they wanted to be a scientist. In fact, I'm a little suspicious sometimes of people who say they always knew. But what I want to see is someone who never gives up. I want to see someone who is persistent and shows up and keeps trying and questions themselves. Those are the things that get you to some goal in the end. And for me, those years I spent, I guess, 8 years in business before coming back, teaching for 2 years and then going back to the PhD, were priceless in learning about how groups of people work together in business with a common goal. And I realized back in academia that there isn't so much of a common goal in your typical research university. Each person has their individual goal. It's a collection of city-states like Italy before it was united. And I wonder, did you also feel that sense that you were supposed to know from the beginning where you were going? And if you didn't want to be a top research scientist, you were somehow settling for less?
Well, I left academic science after finishing my PhD and never looked back, actually. I went into science publishing, started working as an editor of Nature, and became a freelance writer. So, you know, I've never had to pretend that I've had anything like a kind of normal career. But you
must have rejected that narrative along the way, though.
Yeah, I think so. And I think, I mean, in retrospect, I think at the time I realized when I came to the end of having done my PhD, I felt, well, I could probably manage to get by, you know, continuing with this. I don't think I'm ever going to do anything special in science, but plenty of people don't. It's a career I could do. But actually, is that really what, you know, the way I want to spend my time? And in particular, because I'd always written in all sorts of, it had never occurred to me that you could actually combine, you know, I was also a science geek from the outset, but they were two different worlds. I'd never imagined that you could actually bring them together until that point. And I enjoyed writing up my PhD, which most people hate.
That's a great thing to be able to say. I love that.
Exactly. Well, then I thought, well, that's telling me something, you know, maybe writing is what I need to do. So, yeah, it was a conscious, you know, letting go of that. Having said that, I mean, I did have not quite as extensive of time out as you, but I did spend 2 years between my undergraduate and my PhD playing in a rock band.
Oh my gosh, I did not know that. That's amazing.
It was, well, you know, I certainly have no regrets about that, but I had that same sort of feeling of, you know, if I leave it too late, I'm never going to get back into research. So I had to make that choice then, that actually, you know, science is something I want to continue doing.
So good.
But it was, so I guess, you know, that was not exactly a traditional way of of doing it either.
Interestingly parallel lives here. That's really interesting to me. I didn't know about the rock band part. You know, your writing career has been so successful and impressive. And but I think that for a lot of people, it takes strength to decide not to go the academic route after their PhD, because often their advisors are quite pressing them to go that way. And there's a little sense of failure if you choose other, that it's somehow less than. And so I would also like to change that, because we need the kind of training of the mind that comes with a PhD in every aspect of what humans do, I think.
Yeah, absolutely. Absolutely. However, you did get back to science, and you
I
went to
did.
MIT and did your PhD, and then postgrad at Brown, and then you've got a faculty position at MIT. It sounded like very much to your surprise and delight, but of course,
Totally.
and it was there that you began to work to do this field work. In particular, you were working on flood basalts. Specifically those in Siberia. This was one of my favorite sections of the book, because you tell the journey of this field trip to the most incredibly remote parts of Siberia, and this was, I guess, in the early 90s, when
It's a little later than that, thank God. So they were past the famine stage in Moscow.
Sorry, of course, because but even so, it was it was some time ago when things were, they're not what they are now. And you convey a genuine sense of really working right on the edge of the world, really. That sounded like there's a real prospect of physical danger in what you were doing. They're so remote. So what are some of your most vivid recollections of those trips? And also maybe you can say a bit about what you were going there for. What are these flood basalts? What were you trying to find out?
Yeah, I have to say, first of all, I appreciate the chance to talk about this, because it was just a series of, so I was there 4 different times, and the teams went 5 or 6 times, and just incredible experiences, life experiences. Why was I not afraid? Why was I afraid to go to a scientific conference when I was 21 and willing to get on bullet-riddled ancient ex-Soviet helicopters and fly hundreds of kilometers from any person and camp out and go down rivers? Like, I was not scared at all. I was so excited to be there. And so I would just like to thank Jung and the therapy and everything that helped me kind of overcome my past, because that is the perfect kind of black and white comparison to what happened in my mind in the interim. Well, so in graduate school, I became acquainted with the idea that periodically in Earth history, these fissures open up and these huge amounts of lava pour out onto the surface in this kind of event that, as you rightly call, a flood basalt. Has only happened, I don't know, 16, maybe 20 times in Earth history. Doesn't happen at plate boundaries, like mid-ocean ridge basalts or the Cascades or Japan. Happens in the middle of continents. It's not very well understood. When it happens, it's 1 million cubic kilometers of lava, or in the case of Siberia, 3 or 4 million cubic kilometers that cover the continental United States to almost a mile deep. So it's a lot of lava. And it seems like at the same time as this happened in Siberia, which was 252 million years ago, way before dinosaur extinction, there was also an extinction event, the largest in Earth history. Almost more than 90% of species in the oceans went extinct, and over 70% on land. It was close to the end of multicellular life for a little while. It was a very big deal. And lots of people had said these two must be related to each other, but no one had really proven that there was a connection. And other people said they're not related, because flood basalts are just calm eruptions like Hawaii. Like, you can walk up to them and you can go home and you didn't die, unless the lava actually rolls over you. And so we decided we wanted to solve this. And we got a big grant from the National Science Foundation. It was my first big grant success. And at the time, it felt huge. It was a 36-page proposal and $3.2 million. And so now with Psyche, that seems like a walk in the park. But at the time, it was a very big deal. And so 30 scientists from 8 different countries, and we worked on this project for 5 years and had an extension for more year or 2. And it involved going to Siberia and getting pieces of the rocks. So that's what I got to do, that part of it. And one of my most, there's so many vivid moments. One of my most vivid moment was at the end of our first major field season was 2008. And I'd been there previously, but this was a big one up in the Taimyr Peninsula in the northern part of central Siberia, up above the Arctic Circle. And we were going down this big, cold river called the Katui in these dire little inflatable boats. And we'd been dropped there by helicopter, and there were no roads and no railroads. and only one settlement that we passed. And when we got to that settlement, then we pulled out and we got picked up by another helicopter and dropped inland to a place even more remote, where we were the very first Westerners ever to go to this location. And it was just like everything, every day was a series of astonishments with this beautiful giant countryside, which felt, I don't think I might have written this in the book, it felt like my understanding of the earth was not big enough to encompass what I could see with my eyes across the endless rolling taiga, which just goes on farther than it seems possible. So at the end, we've got hundreds of kilograms of rock samples, and our colleagues, our Russian colleagues, managed to get us like a freight flight on a plane instead of a passenger plane, because it's hard to get rock samples onto Russian passenger planes. So we're waiting in the little wooden airport in Hattanga, this little tiny town, and we see our rocks are in a shipping container, and we see the shipping container go out to the plane, and then they say it's our turn. So we walk out around the plane, and we have to climb up a ladder that's leaned against the plane, and there's a rope with knots in it that we're kind of holding onto while we go up so we don't fall. And this always happened. We got in the plane, and there are already people in the plane, which is weird. How did they get there? You know, we seem to be the only ones coming out of the airport. So there are about 8 jump seats that can be folded down off the sides of the inside of this otherwise empty freight plane, and they're all taken. So there's no seats for us. And it's cold, and the floor of the plane is a steel plate. So we put on all of our expedition equipment, you know, our extra layers and our waterproofs and our wool hats, and we're freezing. And the only thing we can do on takeoff is stand up and link our arms around these metal poles. There's a navigator sitting at a desk and plotting things with the protractor. I just feel like, where am I? And so we've got to fly about 4 hours to get to the next, to get to Krasnoyarsk in the middle of Siberia. And partway through the flight, we start smelling this kind of like weird greasy smell. And so I'm there with a couple colleagues, and also Ben Black, who was a graduate student working with me at the time. He's now faculty at Rutgers. And he just was in such a great humor all the time. He thought everything was hilarious, just like I did. You know, he fixes his video on me and he goes, "Lindy, we're about to take off in a plane. We have no seats. Quick, write a haiku." So we're doing this. So we get up to look around the plane. Where does this smell coming from? We go behind the shipping container, and the whole back of the plane is stacked with flayed, frozen caribou carcasses from the ground to the ceiling. They were on their way to restaurants in Moscow. And so we took pictures of them because we could not believe our eyes. Like, they weren't wrapped or anything. They were piled up like cordwood. And so after having been in Siberia for several weeks, and just the occasional sat phone to my, long-suffering, fabulous husband back home, the very first picture he gets from me on my phone when I'm back in civilization is a giant pile of dead caribou from the back of this plane.
I mean, that's exactly it. The plane aside, I had sort of have a sense in that section of the book, it could be happening at any time in the last century. It could be happening in Dostoevsky. It's really
that way. I felt that way, and having been obsessed with Russian writers and read, seemingly all of Tolstoy and Dostoevsky and Pushkin and you name it during high school and college, I felt like I was living it, which made it a fantastical adventure.
Yeah, no, it's that was so fantastic to read about. Well, thank you. Now, I wanted to, in the time we've got left, I wanted to have a talk about what you have to say in the book about how science is done, because this, we've spoken a little bit about that already, but this again was one of the such a valuable aspect of the book, because you're really challenging some of the ways that it's done now, and I think in ways that are vastly overdue and absolutely and hugely important. You say in particular this phrase that you say asking questions implied ignorance at MIT, and I think it's generally elsewhere, and you say at seminars their questions were swords, not magnifying glasses. And again, this absolutely reflects, the experience that I've often had in seeing scientists work, going about their business. And again, it is so peculiar when such a big deal is made in science about how important, scientists ask questions rather than relying on dogma. And yet sometimes it seems that the training that scientists get there's no training for actually the art of asking the right question. There's training about getting the techniques for answering questions, but it's coming up with them that's the important thing. And you have a great section of the methods that you've developed and field tested with students to try to get a better system for how to ask better questions. So can you say a little bit about that, what that system is?
Thank you. My favorite topic. Where are we without questions? And you go through the science classes you have to take in middle and high school, give you the impression that everything is already known and it's in a textbook. What we really have is so many more questions than we have answers. And there's room for all of us to go help answer them. And so, but instead you think that everything is done, signed, sealed, and delivered in a hardcover book, and there's no room for you. So we have to relearn how to ask questions. We've developed with this little company that we started, Beagle Learning, and then my colleagues here at Arizona State University, a new kind of style of inquiry class where the entire class is led by the students' questions, and where they practice asking research questions that allow them to do an aliquot, one moment of research in the form of finding a peer-reviewed paper, understanding what they can of it that answers their question, asking a new question. It turns out this is transformative for people because they've always had their material curated for them in education. And so everything they read, they're responsible for learning, and yes, it'll be on the test. But in the real world, you're asking a question, it's possible no one has answered it. It's likely that someone has answered a part of it. And then when you find whatever they've written or produced, only a part of what they wrote or produced is relevant to your question. So you need to also learn how to dig through the material. That is quite a shock for a lot of students. They've never had to do that. And so in the course of the semester, they learn how to ask better and better questions. And after they've practiced a few times, we give them a rubric. We've actually developed a rubric for what makes a great research question. And we show them how to score their own questions. And then that helps them to improve their questions, to make them more answerable, more specific, more on target for their big goal, whatever it is. So we practice that. And the graduate students who take these courses also have said that they're useful. And I then started working on, in our project here at ASU is called Interplanetary Initiative. It's called Interplanetary Initiative. And one of the things we do is seed fund research projects. Only I don't want people to come and bring their own proposals for their own work that they're going to do, which is the next slice of knowledge in front of them in their real estate. I think that a lot of that research is brilliant. I'm all for the individual researcher, but I think we also need to do another thing, which is aim for the very most important questions and get there as fast as we can, rather than just necessarily having the next curiosity question that's easily to hand. We're in a little bit of an urgent situation in our society. And so we brainstorm together as a group of whomever is willing to come, the very biggest, most important questions that need to be answered in whatever topic we're considering. And then we vote on them. And then we volunteer into groups and see if we can make a project that would take us in 1 year a step toward this giant aspirational question. And then if we can get that far and find someone to lead it, we give them a little bit of seed funding. It could be just $5,000 or $15,000. USIS ended up being very successful. We've now seed funded 38 projects over 7 years. And we're still running at about a 7 times the return on investment where they get follow-on funding from grants and philanthropies to continue the work. So trying these different ways to help people ask questions, overcome the hero complex, work in teams, go for more important things. These are our little ways that we're hacking away at that mountain.
Well, I think what's so valuable about it is that it's one thing to say, wouldn't it be great if we did things this way? But actually what you're showing is that there are systems that you can use. It's a teachable thing. Asking questions is a teachable thing. I mean, I feel the same way about writing. Scientists are somehow magically know how to write, and it's and either you're good at it or you're not. But that's absolutely not the case. It's a craft that you can learn, and it's teachable. And I think that's one of the lessons that I took away from your book, that so many aspects of science are supposed to be like team building, like leadership, like mentorship, that they are things that either you're supposed to somehow get if you think that they're important, but no one's going to teach you. No one's going to tell you how to do these things, and yet they're central to doing science. And I think it's so valuable to show that actually they are teachable, and they should be taught.
You must have seen so much of that at Nature, how teachable is writing and who's been taught and who hasn't. So many examples. And yeah, and I see this actually a lot in the highest levels of competitive science and engineering. The idea that the hard thing is the science or the engineering, and everything else about your craft is something that you're smart enough to teach yourself. So we are smart enough to learn on our own how to write, how to mentor, how to write budgets, how to deal with HR issues, how to form teams, how to be a leader. These are actually really difficult things that it's possible to learn from other people who know more about it than you do. And so that's a little bit of what we're trying to bring to the table also, like you are with writing.
Well, and I feel not doing that creates huge impediments to science. A number of times I see papers that are, they're not difficult to understand because of the concepts. They're difficult to understand because the people who've written them clearly have had no training in how to do an idea. And it's not their fault, of course. They just haven't had that training. But that's if you don't have that, I mean, and I see it all the time, scientists are talking past each other simply they have skill in or practice or training in how to communicate effectively.
That's right.
Yeah, and one aspect of that, and then one thing that really struck me in your book as very, very familiar, is you say that you see graduate students learning how the game is played at the moment, which is to make confident, assertive statements, whether it's right or wrong. It's about putting someone else's ideas down and saying, no, this is how to do it.
That's right.
It's a very depressing thing to see, as you say, that you can see that happening, that people don't come into science thinking that's the way to do it. They learn that that's what is expected.
That's right. Yep, that's right. That's right. And I've had these arguments with postdocs and graduate students over the years a number of times where I tell them to please not use jargon in their talks and please remove their acronyms. And I've had people say to me explicitly, but if I don't use jargon and acronyms, how will they know I'm an expert? Won't they just assume I'm not good at what I do? I think that it's so central to be a communicator. And in the end, I did leave that position at MIT to go to Carnegie and to come out here. And it's a little bit of an unexpected step to go from the Carnegie Institute and MIT to ASU 10 years ago. But really what brought me out here was the vision. It was the vision that we could educate those who were educable instead of only allow in those who were already excellent. And to me, that is a part of this whole thing that we're talking about, the idea that you can learn these skills and that these skills should be available for everyone to learn. And it turns out that starting with a populace that isn't already convinced that they're brilliant, it's a little easier to make progress.
Right. Yeah. And okay, yes, and there's a very powerful section in your book that also sounds so familiar about dealing with harassment and bullying, which is now recognized as a huge systemic problem. I mean, not just in science, of course, but it is very much there in science.
That's right.
And you have an account of a pretty horrendous episode that you had to go through, where there was a reluctance to do that, and I think it feels to me again as though science, it's as though that idea conflicts with the the lone creative genius, that they're given a free pass for so much sometimes,
including things that are literally illegal. That's right. That part of the book that you're talking about, luckily I was not the object of the harassment particularly, only a little bit, but just trying to make change as a leader. And this is, we talked in the beginning about being a woman in science, and obviously there is a huge gender bias in general in humanity everywhere in the world. But I'm much more concerned about anyone who isn't feeling like they are the strongest person in the room, or that they have a cohort that they consider to be like them. Men who are sexually harassed have fewer resources and less help than women who are sexually harassed, who already have little enough. And so this is a all community problem. And it has to do with power dynamics, which feed into everything we've just been talking about, much more than it has to do with sexuality. And so it's a symptom of the culture that we've been discussing.
Right. Right. And you say that it's perhaps made even more difficult now by the fact that you have this very interesting phrase that sometimes students seem to be arriving in courses pre-enraged because of what they've already experienced. And, that just means passions get inflamed, immediately, and it becomes harder to resolve situations, amicably or at all.
Yeah, that's ended up being a very useful concept for me, the pre-enraged. And, once people are allowed to really recognize the wrongs that have been done to them in the past and understand that they are wrongs and see that they were not righted, there is this rage, and rage is the result of feeling impotent against what's wrong. And people do tend to bring that emotion with them to the next similar circumstance. The challenge, and I'm certain that you faced these emotions many times as you had to give people bad news about work that they were doing, whatever it was, like that's not a pretty process to go through with academics. The challenge is that when it comes conversation about a difficult subject already attacking, it does not motivate the other people to come to a negotiation and a good solution. You have to take that page from Ruth Bader Ginsburg and become the kind of leader and change maker that other people actually want to work with. And it requires a lot of control. And it's very hard for anyone trying to make change to deal with all the people who are furious, not at the person trying to make change, but really at their past.
Yeah. Okay, well, I think we're probably meant to wrap up on the hour, so I'm going to do that. But I do want to finish with the big event that's coming up, the impending launch.
Yeah.
I cannot imagine how tense it must feel for you, but I'm going to ask you, what do you feel like at the moment? I mean, do you feel confident? Do you feel ready for this?
I feel ready, but not confident, because I think confident is a thing that one should not, it's too close to complacent. Right. So many things could go wrong. Like we actually find new issues all the time, like every day. We're just a few weeks out. And so I'm glad that you asked it that way, because a lot of people ask me, aren't you excited? And I hope to be excited one day. Right now we're just trying to do the right thing and get there and stay focused on what we're doing. And I think a really important part of the story is that we were supposed to launch last August and we were not ready. And the reason we were not ready, there are many reasons. It's a complicated thing. If we knew exactly like the one thing, we would have fixed it. But there was a part of the team where team culture failed and where people knew something was wrong and they were not able to speak up because their leadership did not listen. It was unfortunately the proof through failure that team culture is everything. And so they were not able to finish on time. It was not their fault. They were under-resourced. They were not listened to. It was our fault. It was the leadership's fault. And that was a very expensive and painful error. And now we're getting a chance to launch again. And we've done all that work and made it up. So a year of lessons learned, of huge pain overcome, amazing challenges this team has come over time and time again, building the spacecraft during COVID. And I'm confident we're going to launch in October and it's going to be amazing. And then I'll be super excited. I'll be super excited when the spacecraft is power positive, thermally stable, and in communication with the Earth. Then there will be lots of jumping up and down.
Well, all I can say is the very best of luck with that. And I felt the same way with the JWST, that having spoken to people involved and now having read your book and spoken to you, I feel so invested in this myself now. I'm really on the edge of my seat.
Part of the team. You're part of the team. I'm so grateful for your time and attention and for the opportunity to speak with you. Thank you so much for this.
Oh, it's been a great pleasure. Thank you.